Hey YouTube, so I'm back with another video here, and I'm on the floor instead of at the table this time because I don't really have space at the table to set up my camera there, but I wanted to do this video because I got a really awesome piece of equipment given to me yesterday by a really nice guy named Bob Godin. I was telling him about some of the stuff I was doing, and he had an oscilloscope left over from when he used to be at college. Apparently, they were updating and getting rid of the stuff, and he ended up with one of those oscilloscopes, and he's had it for years and years and years, and now he's passing it on to me so I could use it. And this is really amazing because these are not cheap pieces of equipment. So I'm really grateful to have received this. Okay, there we go. Bit of a trick to undo the lock. So yeah, so let's check out what's in this box together. So right away we have a bag with a couple of different probes on it. You have 3 positions on the switch, times 10, times 1, and reference. We'll leave that there for now. And over here we have a little bit. Okay. It's completely upside down. So let's turn this upside right. And we have here a BK Precision 30 megahertz oscilloscope, model 1474. Now I'm sure there's going to be at least somebody watching who remembers this thing from back in their younger days. And I'm excited to plug this thing in and see how it works. So this should be awesome. Okay, so let's get a probe on here. Interesting button. Oh, here's an end piece there. Basic probe here, X1, X10. Again, I can't say thank you enough to Bob for this piece of equipment. This is a really wonderful thing to receive. I'll fiddle with that later. I think for now, I'll stick this in here. I think for now I'll just stick with this probe here. I'll put it on X1, and we'll get this thing plugged into over here. I can see we've got the first channel, channel A. It's got a 1 mega ohm resistance. And it says it's got the roughly equivalent sign, 22 picofarad. We've got ground, DC and AC coupling over here. Here's where we can set our voltage per division. In terms of the channels, I can either add them together. I can have dual channel, or just channel A, or just channel B. For now, I'm going to put it on just channel A because that's all we have to worry about here. Okay, and then we need the, well, we don't actually really super duper need this ground clip, but it's handy. Now, let's see where the power switch is. So we are in the off mode now. And power up. Okay. There we go. Check it out. we have a wave. And if I touch it with my finger here, we have a bigger wave. Cool. All right, so we can adjust the position over here of where the wave is. We've got focus, so we can get this lined up correctly. We have intensity. Of course, we want a decent little brightness set here, just enough that we can see it. And then, oh, we have power illumination. That's what this is. This is a light for the front of it here. For the time, we have different sweep times, so we can actually sweep all the way up. Look at that. We can get to half a second for the shortest sweep time. And for the fastest sweep time, we can go all the way to 0.2, so 200 nanoseconds for the sweep time. But over here, we'll stick with, we'll do a, oh, and we can adjust up or down within there. Oh, that is so cool. Check it out. And you can see, doop, it reminds me of a heart rate monitor. Now if I touch this with my finger over here, obviously you can see a much larger signal going by. So, let's see about the triggering. I'm going to have to talk to my to one of my other friends, Dennis, and show him this and get him to... there we go. Now I've got the signal coming down. Triggering level needed to be lower. I was overdoing it before. Positive or negative slope. Coupling, we can get high ref, low ref, DC. I'm going to put it on AC coupling. The source, we want channel A. And we'll leave that on auto. Position, pull, 5x. Oh, okay, so we can adjust where the start point is. We'll put the start point at the start of the graph there so that we have the sweep go across the entire graph. Position over here, what is this? Okay, this is for, I don't see much of a difference there. And I'm sure I'll figure it out later. We have a little 1 kilohertz square wave calibration over here. I'll need to pick up a little jack so that I can actually use that calibration signal. Did I miss it maybe? Okay, no. So, alright, well let's get this up to the midline here. And so what you were seeing before, when I stuck my finger on this, was actually, that was actually, oh, and I'm in millivolts, that's why. Let's stick this into 1 volt per division. No, that doesn't show up. That doesn't show up. There we go. You can sort of see it at 0.1 per division. And let's put this at 50 millivolts per division. There, you can sort of see it now. Now, if I increase the intensity, will that let it stay longer? Not quite. Okay. Let's see if I can't get the focus to be a little sharper. There we go. Now we have a sharper focus. And okay, that's good there. The sweep time is good. Okay, so that's how this one is going to be working out. So the persistence on the display is as long as what you see, and that's fine. That just means that this is going to be what we're going to be using to read with this. Now, as a fun little part of the test here is I'm into energy harvesting, all kinds of energy harvesting. And so what I've got over here is a little receiver coil that I wound. So I 3D printed this. It's got 30 wraps of wire going around this. There's a little bit of spacing between all the different wraps. And then I wanted to make sure that it was going to be push-pull. So I have a little toroidal core here. And I did wraps around this little toroidal core so that hopefully this would end up being a push-pull. But I get some odd behavior with this. I'm not 100% sure why, but you know, I'm an instrumentation and controls engineer, not a radio engineer. I'm just interested in energy harvesting as a hobby. So let's see about hooking this up here. So right away, hooking this up, you don't really see much of a difference. Let's put this on a slightly higher voltage per division. So right now we're at 10 millivolts per division. Let's see if we get a change. Now you see that? So we do see a change. So let's get this centered again. This is without the wire attached. This is with the wire attached. So you can see that we're picking up, this is 10 millivolts per division. So we're actually picking up somewhere in the vicinity of 40 millivolts peak to peak. And the odd thing that I find though is if I put the ground on the other side, it goes away. Why? If anybody in the comment section knows why, I would like it explained, because from what I understand about electricity, if I have a core here and I've wounded, I wound these two wires together on this core so that if current goes through on one direction, it has to get pulled through on the other direction. And then furthermore, like it's only one piece of wire. If I'm getting plus voltage on one side, I should be getting negative voltage on the other side. So, like, that doesn't make sense to me. You would think that if you got a positive voltage signal on one lead, that you should get the opposite voltage signal on the other lead. But hey, it is what it is. So the way that it works out is any sort of little energy harvesting, whatever you want to do, it's just going to be solely off of one lead. And you can see here, if I touch the other lead, I get a better voltage signal because my body itself is actually a very wide band and very effective radio antenna. And then something else that's even cooler is if I touch, okay, no, I'd have to get a grounded wire. But if I put a grounded wire on the ground lead, then that voltage signal gets way bigger. And just to show you that this energy harvesting stuff is it's so cool. I've got a little breadboard over here. And I got some wire I can use over here. And on this breadboard I've got some LEDs, and I've got this little capacitor here, which I'm going to take my leads here. I'm going to drain that capacitor because it kind of defeats the purpose of my energy harvesting experiments if I start with a fully charged capacitor, and show you that you can actually do some interesting little bits of energy harvesting with this. Now, to do the actual energy harvesting, you need to use the right components. So what I have over here is I have these BAT 46 CT-ND, or actually here, BAT 46TR. These are germanium Schottky diodes, and the reason that I call these the right components is because they actually have a voltage drop that is suitable to be used for energy harvesting purposes. So you can make a full wave bridge rectifier, and you can do so with the highest possible efficiency. So get 2 diodes to bring the positive to the positive, and then another 2 diodes. These ones are going to bring the negative to the negative. And of course I don't actually need this for the charging purposes that I'm doing right at the moment, because I'm only going to use 1 lead off of this. So just to show, I'm going to disconnect this one over here. These 2 leads are tied together. If I touch them, yes, there's a bit of a voltage signal going on there, but that's mostly because because I'm touching it, and I'm a really big antenna. Now, let's see here. We will get our trusty little fluke multimeter here. Sticker on millivolts, and the ground goes in the ground, positive goes in the positive, and you can see that we have a very slight amount of millivolts that are there. Now it is going up, and the reason, a big part of the reason that the millivolt rating is increasing there, let me short out these 2. The reason that the millivolt rating is increasing is because germanium diodes are actually subject to some thermal excitation just from the environment, the heat in the environment itself. So they are actually providing some of the charge. But now I'm going to flip this around, because when I stuck it in, let's see here. Yeah. Okay, let's short this out again. Leave it shorted for a second. There we go. Alright, so I'm going to reverse these leads because I built my my rectifier backwards. And now we'll take, and you can see this is going to be charging up a little bit. Let's see if I turn on the light. Maybe you guys will see it better from that. Alright, so you see a bit of thermal excitation from the germanium diodes charging up the meter here. Now if I take 1 lead from my receiver coil and I plug it in, we should see an increase, especially if I touch. Of course, things don't work when you're trying to show them off. Gonna make a liar out of me. But, okay. Anyway, now we can take our oscilloscope here, plug it in, and we can see that we are at least picking up a little bit of a wave coming in. just a few millivolts. And with our lead from the oscilloscope attached to the negative there, just taking the measurement, you can see that we're actually increasing the voltage coming out. If I had a ground nearby, I'd plug it in, and then we'd actually get full radio antenna functionality, and you would see a much larger voltage drop. But I don't really. The only sort of thing that would be even close to that would be, actually, I could use this. There we go. So I've got this this DC power supply here, and the power supply itself has a ground lead. So I'll leave the power supply off, but I'll plug it in so that we get the ground from the wall. And we will grab another piece of little wire here and stick it in the negative, which I've actually got over here right now, and attach. So now we would actually probably want it to be over here, but what you can see is we can pretty consistently pick up just off of this position like 40 millivolts. If I raise this up, move it into a different position, you see that I can pick up more voltage. Yeah. Let's turn on the light again here so you can actually see. But 50 millivolts to charge this 100 microfarad capacitor. If I put it down, the charging stops. Actually, it starts going down. If I raise it up, the charging resumes, continues to go up, and so on. So you absolutely can do some RF energy harvesting. Now, if I were to now take my oscilloscope here and check, well, what kind of frequency is doing the charging. Let's see here. Try not to get this to go out. And I can see the ripple coming in here, but I need to change the coupling to DC. Now I can see the DC ripple. I'm at 10 millivolts per division. I'm almost up at a charging rate of 60 something here. I guess it's because, oh, that's right, because I'm seeing the voltage after it gets subtracted by the, yeah. And we need AC coupling to read that correctly. So one way or another, we can see that there is power coming in. Let's compare what we're seeing here with this oscilloscope to my my more little modern solution that I have here. So so the one that I was using, let's also make sure that, okay, it is on 1 volt per division. Let's see what my other oscilloscope reads. So this is an FNIRSI, I guess it's FNIRSI, it would be how you say it, oscilloscope. And I've got it here with channel 1 set to, let me just make sure, channel 1 is set to 10 volts per division, or sorry, times 1 scale, I should say. The coupling is set to AC. Alrighty, so now let's see what we pick up with the FNIRSI. With the Furnace C, we are going to set this here. Click the auto. And we don't see much of anything on that scale, or time scale. Okay. Let's see what we see when we attach to the input side of this leg. Hit auto again. And again, oh no, you know what would really help? It would really help if I plugged this into the correct port. That would help a lot. Here we are. So let me expand this for you guys to a higher volts per division. But this is the incoming wave here. And you can see that it matches what we were seeing with the other device. We'll decrease the volts per division, or the sweep time here. And now somebody might be like, oh, well, you're picking up wall frequency. You're just getting what's coming through the walls. And you would be right, except if you read on here, we can see that the frequency, though it is regular, it's not really matching up with the wall frequency. I'll increase the sweep time here. Let's see, we'll adjust it to the longest sweep time. So at the longest sweep time, it looks like this. We can't actually get any useful reading off of it. So the next, if we put it so here, there we go. So you can see we're picking up like 30 to 47. It's like reading between right around like 40 hertz. So whatever it is that I'm harvesting right now, I'm picking up a 40 hertz signal. And there's all kinds of signals like this in the natural environment that you can pick up and harvest. Specifically, there's the voltage signals around, well, anywhere from like 7.8 to 200 hertz. There's actually a huge amount of electrical noise in that frequency range. That's actually really high on the dB scale. So that's a lot of energy that's flying around. That's just available to be harvested. And then if you're looking at a spectrum graph of the noise floor, there's also another peak that happens at about 5 kilohertz. And so that's another really great frequency to kind of target and go after. Now obviously this is not a tuned resonating setup, but it is putting out a signal. It is picking up something, and obviously it's picking up something that it can charge a capacitor with. So one thing I do notice when I play around with this is the higher I lift my antenna relative to the ground position, the more voltage I get. And so a project that I have in mind for later, when the snow is not on my roof and it's a little bit safer to go up there, is I want to put an antenna on my roof, either a single line strung across the length of my roof, or I'll make a mount for this and put this up on my roof. And I should be able to get more than a volt with that kind of differential. My record for using radio antennas to charge a capacitor is about 7 volts, and in one experiment that I had done with one set of antennas that I had done, I was able to persistently light an LED. Now I'm hoping that if I put the antenna on my roof, I might actually be able to persistently light an LED to a reasonable brightness. You know, maybe I might be able to collect a few milliwatts, or maybe a couple hundred milliwatts. And then it would be very interesting to characterize, well, how much power, how much energy am I capturing per unit area or by unit volume with these antennas. And which then leads me to the other question, would be like, would a large antenna receiver array be able to collect a reasonable amount of power? Like if I was to create one antenna, say a line antenna, and I was going to string that across the length of my roof and rectify what comes off of that to ground. Well, if I placed another line of antenna going along the length of my roof, how close, how far apart could those antennas be before they start interfering with each other and sapping away the energy that the other one's trying to pick up? And based on how close they can be, what kind of density of positioning can I get? And how many milliwatts can I get from one antenna? Because if I can get, if I can spend $10 and run an antenna line across my roof and pick up a couple hundred millivolts or milliwatts, or potentially 1 watt with one antenna line, if depending on the density and how you string it up, well, how many watts would I be able to pick up if I used my whole roof? And then how does that compare to the energy density of solar? That would be a really big question to me, anyways, and something that would be interesting to find out. So, like I said, later on, I'm going to be stringing up a line and seeing what I can pick up. Until then, see you next time, YouTube.